It is my great pleasure to introduce Mihaela van der Schaar. She is one of the experts in applying machine learning and AI to the field of medicine. She's a John Humphrey Plummer Professor at the University of Cambridge. Her group is working on cutting-edge machine learning and AI theory and methods with the goal of improving healthcare and medical knowledge. So they are one of the most impactful and diverse teams in their respective field, and they're employing a wide range of machine learning algorithms, including deep learning, causal inference, which is going to be the topic of today's talk, AutoML, time series analysis, ensemble learning, and many more. So Mihaela, the floor is yours.
Thank you very much, Maziar, for inviting me. Really a true pleasure. I'm going to minimize everyone from my screen, but feel free to interrupt if you have questions. And if not, I will take questions at the very end. I'm also going to... Okay, so what I'm going to talk about today is the topic of causal effect inference and counterfactuals. And I'm going to provide a machine learning approach view to this important topic. I'd like to start by thanking my research team, my postdoc, and my PhD students working in this area, without which this would not be possible. So our group's research is focused on developing methods that can help move medicine from an art towards a science. And the focus is of developing technologies to deliver bespoke medicine, understand the basis and trajectories of health and disease, empower healthcare professionals and patients, inform and improve clinical pathways, better utilize resources and reduce cost, transform population health and public health policy, and last but not least, enable new discoveries, both in a clinical setting, but also new therapeutics. Our group is focused on developing machine learning methods to enable such a transformation in healthcare. And I'm going to first outline several of the topics that we work on. First, a key challenge in machine learning for healthcare is that the data sets that we would like to develop methods on are not widely available, and they often cannot be shared among researchers. So one important area of research in our lab is to develop synthetic data generation models that have high accuracy, but also fulfill privacy constraints. So we are focusing on developing generative models that have, for instance, different types of privacy guarantees, inclusively differential privacy. So we have a big agenda in this area of synthetic data generation. And we hope that if we are able to generate this synthetic data with high fidelity and provide guarantees associated with it, we can then develop as data scientists, machine learners, methods on the synthetic data sets and then port them once they are developed into the real data sets where they are going to achieve a very similar performance. We also develop a variety of analytics. Today, I'm going to talk about individualized treatment effect inference, but we work also on time series data, missing data, transfer learning, AutoML, and a few others. In order to have really actionable intelligence that clinicians and patients can use, we need to make sure that these machine learning models are indeed interpretable and also have uncertainty quantification associated with them, such that the users of these models know when they can trust the model and when they cannot. So we work on interpretability and uncertainty quantification as well. Another topic that we are working on that we call quantitative epistemology, and that is a name we made up, is to focusing on understanding from data how humans, especially medical providers, actually learn and make decisions. So we learn from data the decision-making process of individuals. And a lot of recent research in our lab is focusing on that. And maybe if I come in person one day, I would like to tell you more about this particular topic. I'm going to briefly touch upon it at the end of this talk, but more about it to come. This is important because if you are interested to understand variation in practice, both desirable variation as well as biased, undesirable variation in practice by clinicians, we need to understand the basis on which they make decisions. This is also important because we would like to understand the human in the loop and what is needed to understand from the decision process in order to create, design, and debug methods that are truly useful to enhance and empower clinicians and patients. So there is a lot of interaction between this decision-making of humans and the various blocks to which we have worked in the past, and we are continuing to work. Today, I'm mainly going to talk about individualized treatment effect inference because this is a very hot area of research where researchers from applied mathematics can contribute a lot. And it is a really ongoing area of research where a lot of new good ideas are necessary. Before I go into the details of that, let me also say that we are working a lot with clinicians and healthcare professionals, and we have a variety of engagement sessions, inclusively something that we call Revolutionizing Healthcare, which is an engagement session where we engage with clinicians to understand the problems they would like solved. So rather than have a machine learning model or a data science model and try to push this technology into the realm of healthcare, we want to go the other way around. We want to understand the key problems and challenges that clinicians are facing, and informed by these challenges and requirements, define new methods that are truly useful for them. You can take a look at these sessions if you like and see some of the conversations that are emerging. One area where we are working a lot on is cancer. And cancer is a complex disease where there is a lot of need for decision support. Let me just give a few examples. In order to identify cancer early, we need to determine how to screen patients and how to acquire information over time. This needs to combine ideas from operations research with ideas from machine learning in order to identify a cost-effective way to do screening in a personalized way. In the area of treatments, I'm going to talk quite a lot about today how we can select the best therapy to be giving to a particular patient given their unique characteristic. And then as the patient is evolving through their disease, what type of interventions we should make over time to prevent a relapse from the disease. Also, you see once in a while the word clinical audit. The focus there is to understand why certain medical centers, for instance, are very successful in treating cancer and some are not. Trying to understand the decision-making process of clinicians using these tools from quantitative epistemology and trying to understand whether we can apply this decision-making process in another setting. Together with Public Health England here in the United Kingdom, we have developed a few years back a decision support system for cancer to highlight what is possible using machine learning to assist clinicians and medical researchers treating patients with cancer. If you want to take a look and see more about the realities of the data, how the data looks like and the challenges associated with it, as well as see our demonstrator, you can take a look at this Turing talk that has been given by me and our collaborator from Public Health England. Today, I'm going to only focus on one particular aspect, personalized therapeutics, where the goal is to estimate the effect of a treatment or an intervention on a patient. For instance, Mary was just diagnosed with a particular disease, let us say breast cancer, and we would like to identify what treatment or intervention is best for Mary. So we want to estimate individualized treatment effects. So we have observational data, including data that was acquired about Mary at diagnosis time, and we would like to identify what is the best treatment plan for Mary. To give a very simple example, shall we give chemotherapy to Mary after a surgery or not? What will be the effect on Mary in terms of, for instance, 5-year survival probability? We also can look at more complicated treatment effects, such as what is the dosage associated, the optimal dosage that we should give to Mary if we decide to give chemotherapy. So here I'm highlighting a few examples, and I'm going to go into more details later. One can also look at multiple treatments, for instance, chemotherapy and radiotherapy, or treatment effects over time. What type of treatments and intervention should be given to a patient as their disease is unraveling over time? And look at not only short-term outcomes, but long-term outcomes, as well as a variety of endpoints that may look not only at survival, but also at side effects. Usually, when patients are treated, current treatment decisions are based on randomized controlled trials. However, it is well known that the treatment effects are often heterogeneous across the patients. So while, for instance, for the average population, giving radiotherapy and chemotherapy may be the desired choice, for Mary, it may be that chemotherapy alone leads to a better outcome. So a limitation of the randomized controlled trial when we need to think about treatment effects at the individual level is that they are focused on average treatment effects at the population level. And usually these RCTs are only enrolling small sample size, not representative patients. So often patients that are elderly or patients that are very young or patients with comorbidities are not enrolled. Also, these RCTs are often focused on a very specific question. And in reality, we may be interested in different types of endpoints and different types of endpoints over time, inclusively the quality of life of the patient and how it evolves over time. And also, these methods often are unable to capture the complexity of caregiving. In addition, they are time-consuming, costly, and at times running them may also lead to ethical issues. So as a complement to randomized controlled trial, not a replacement, but a complement, I'm going to talk about learning individualized treatment effects from observational data. So data that comes from electronic health records or disease registries, such as cancer registries, which focus on estimating effects of treatment for a specific patient. The advantage would be that in this case, we can learn from large sample sizes, so large data set, which include representative patients, capture many aspects of care. And if we can do that successfully, then we can learn these effects in a fast, inexpensive way and with implementations that are scalable and adaptive. What type of data do I have in mind? So observational data is collected from actual clinical practice, which contains patient features, treatment assignments, and outcomes. Here I'm going to consider a very simple setting to formalize the problem, but the reality is that some of the algorithms that have been developed go beyond a binary treatment. So here I have a treatment assignment variable W, which is just treated or untreated for a patient, but the reality is that this could include multiple treatments as well as continuous assignments, such as dosage, so continuous treatment assignment. What is important to note for observational data is that this is unlike in a randomized controlled trial. It does depend on clinical practice. So the doctors do not close their eyes when deciding to treat a patient. They have their own biases in deciding the treatment, and this leads to selection bias that we need to deal with. So we can estimate, for instance, propensity functions associated with giving a type of treatment to a patient given their unique characteristics X. Another challenge from estimating from individualized treatment effects from observational data is that we do not have counterfactuals. So we only observe what has happened to the patient given the treatment given. We do not observe what would have happened to the patient if we would have treated them differently. We never observe counterfactuals. So this represents a complicated machine learning problem, unlike in the supervised learning setting, where the focus is on just making predictions on the basis of the data. Here we want to estimate these counterfactuals to be able to estimate individualized treatment effects. So in order to estimate the treatment effect, we need to somehow estimate these counterfactuals. We also need to model effectively interventions. So how shall we use this variable, this treatment assignment, and how shall we design models to include this assignment variable is an important challenge to address. And as I mentioned before, we need to deal with selection bias, also known as covariate shift. So this problem needs to be formalized as a causal inference problem, where we have patients, interventions, and outcomes, and we try to estimate the effect of a treatment on a patient given different types of treatments. A variety of approaches exist to solve this problem, and one of my favorite books in this area is the book by Hernan and Robbins that talks about a variety of ways to think about causal inference. And extensive works exist in statistics and econometrics in this area. Today, I'm going to give you a machine learning approach view to this area, and I'm going to highlight what I believe that machine learning can contribute to this important agenda. I'm going to cast this problem in the framework of potential outcomes defined by Neyman and Rubin, where we have again patients whose variables are identified here as xi, treatment assignment, and we have potential outcomes, the treated outcome and the control outcome that we are trying to estimate. As I mentioned, we only observe factual outcomes and not counterfactual outcomes. Yet what we try to estimate is this individualized treatment effect. Here we are not going to focus on average treatment effects, but rather on individualized treatment effects, also known as conditional average treatment effects. And I would argue that the conditional average treatment effect is a more correct terminology, but often we use the word individualized treatment effects in the machine learning literature, so this is what I'm going to use here. So given the unique features of a patient xi, we are going to estimate the effect of treating this particular patient. Two assumptions are made in this framework. One is that we do not have hidden confounders, so the assumption of ignorability. The other one is of common support. There are no patients that are either treated, given a particular feature set, that are either treated or untreated. The way in which usually, so there are multiple ways to estimate treatment effects from such observational data in the potential outcome framework. Here I'm going to mention one of them, and that is covariate adjustment, where we explicitly model the relationship between treatments, covariates, and outcomes, and we try to model these response surfaces and estimate the causal effects by modeling the difference between these response surfaces. If we are able to do that successfully, we can estimate not only the average treatment effect, but also the individualized treatment effect. Two key questions in this covariate adjustment setting are: how shall we model the treatment assignment variable W to better deal with this covariate adjustment problem? And secondly, how to deal with selection bias. Different solutions exist, and I'm going to go into them in a little bit, but machine learning really can help this research agenda that has emerged for a long time in statistics and more recently in econometrics as well, by providing flexible end-to-end architectures which can model in a very flexible way the treatment assignment and this covariate adjustment. So that different response surfaces can be modeled effectively and scalably using machine learning, as I'm going to show to you a little bit later. Also, we can deal effectively with selection bias by crafting loss functions that enable us to train any given architecture. And indeed, progress in the area of machine learning for causal effect inference has emerged in the last 5 years. And it started with early work by Shalit, Johannesson, and Sontag, and then a variety of works has emerged, inclusively our own work, some using deep learning, some using multitask Gaussian processes, and a variety of other methods. We have also extended the work to multiple treatments, and there we have used generative adversarial networks, continuous treatments, time series models that I'm going to briefly highlight later, as well as combining pharmacokinetic models with machine learning. And if you want to see the different works that we are doing in this area, please take a look at our website dedicated to this topic. We have nowadays quite a lot of information on our website and also a blog piece about it. So if you want to learn about the topic, if you are not familiar with it, please take a look. Let me now go back to the two key questions that I started with. How shall we model the treatment assignment variable, and how shall we deal with selection bias? A few years back, we started the classification of IT models into three types. One is where we learn separate models for every treated population. So for instance, if we have a treated and a control group, we are going to learn separate models for the treated and the control group. So this would be one way to deal with the treatment assignment variable. Other models are using the treatment assignment variable to augment the feature space. So in addition to the features of the patient, we can augment this feature space with the treatment assignment variable and learn this response surfaces in this augmented feature dimension. A third class enables us to index Schaar representations across the different populations that are treated differently and learn Schaar representations. So learn response surfaces that are indexed by the treatment assignment variable. If you look at the literature, you will see that most of the models, and this is a relatively older slide, but this is still true today, models fit into these three different categories. Separate models augment to feature space Schaar representations. Also, some of these models handle selection bias and some do not. So what is best to do in this case? Clearly, a theory would be needed to tell us what models we should select and when. So this is what we have done again a few years back. We developed the first theory for individualized treatment effect inference that is looking first at fundamental limits and trying to understand what is possible, what can be achieved by any algorithm in the limit, develop an understanding and a theory behind this, and then use that to inform algorithms and understand which type of models would be more successful to really address this problem of individualized treatment effect inference. So how did we go about this? We formalized this problem in the Bayesian non-parametric estimation setting, and we modeled these different response surfaces and we put priors over the response surfaces pi, and we estimate a frequentist loss using a point estimator t hat induced by this Bayesian posterior given the data set D. The error that we want to minimize is the precision of estimating heterogeneous effect, also known as PEHE, which is a metric that was introduced by Jennifer Hill a few years back, almost a decade ago, and is estimating the error in estimating this individualized treatment effect. Why we choose a Bayesian non-parametric approach to develop this framework? Well, there are two reasons behind it. First, it allows us to be robust to misspecification, but also we can rely on very powerful results from Bayesian non-parametric statistics to develop the bounds and the insights I'm going to describe next. So what can be achieved? The focus of our theoretical work was to understand how hard the problem is. So identify the hardness of a non-parametric IT estimation problem. And for that, we are trying to determine the minimax risk, which is an information theoretic quantity, which is independent of the way in which we learn, independent of the IT model. This minimax estimation risk is shown in here. And since PEHE is an error, an error that we are estimating, we are focusing on a best estimate, which in this case is an infimum, over the different response surfaces. So what we are looking at is the minimax rate being the fastest rate by which any Bayesian estimator t hat can approximate the IT function, the true IT function t. So this is what we are trying, it is this minimax rate that we are trying to estimate asymptotically to understand how hard the problem is. In a theorem in this past work, we showed that the minimax rate for IT estimation is given by this theorem. Let me go into the details of this in a little bit, but just in case you are interested in how we prove this, it relies on information theoretic techniques based on Fanos method, but also on results from asymptotic statistics from Ad van der Waart. And we heavily relied on these results to derive this bound. So what are the parameters that are of interest in this theorem? The terms D and alpha, what are they? They are capturing the complexity of the response surfaces. So for instance, D is the sparsity of the response surfaces. How many variables, how many features are going to be impacting the outcome of a treatment? So which variables, for instance, for a particular patient with cancer are going to influence the response surfaces of the treated patients with cancer or the untreated patient with cancers? And it could be that different number of relevant features, so the sparsity is different across the different response surfaces. Another important parameter is the smoothness, alpha, which can be captured by, for instance, a Holder continuity condition. And depending on how rough the different surfaces are for the treated or not treating population, this will play a role in how hard it is to estimate this minimax rate. So as you can see in here, the minimax rate is dominated by this sparsity and smoothness. And to achieve the optimal IT rate, models should be capable hence to incorporate W such that it encodes different relevant dimensions alpha, as well as is flexible enough to accommodate the smoothness levels of the response surfaces F0 and F1. And we need to be able to select methods that enable us to effectively tune hyperparameters. In other words, the smoothness of the prior, to capture this type of smoothness. Also note that this theorem tells us nothing about selection bias. So the minimax rate does not depend on the selection bias. And if you think about it, this is kind of logical because this is in the limit when the number of samples grows to infinity. And in that case, indeed, selection bias usually doesn't make a difference. So at this stage, we can say, well, shall we even care at all about selection bias? Are people wrong to worry about selection bias in these causal effect inference settings? And the answer is that if you are operating in the large sample regime, when you have many, many samples, then indeed selection bias is not going to play a role. And instead, we should focus on smoothness and dimensionality when modeling these response surfaces. However, in the low sample regime, everything is going to be dominated. So this error, this PH, is going to be dominated by this offset. And this offset is nothing else than the Rayleigh divergence. And this is the selection bias. So in the small sample regime, we do need to account for selection bias. So what this theory tells us? It tells us that in the small sample regime, we need to develop methods, whether it's from statistics, econometrics, or machine learning, that do account for selection bias. So models in the class that I showed you before that disregard bias in the small sample regime are not going to be efficient. So you saw some models that are, for instance, in the first class where they are separating the treated and untreated population. That is not going to be very effective because we need to be able to share data effectively between these different models. In the high sample regime, on the other hand, we need to be able to tune the smoothness and sparsity of the priors on the two response surfaces. And models in the second class are not going to be very effective because they are building this augmented feature space that doesn't allow us to treat differently the smoothness and sparsity of the different response surfaces. So because of that, if we want to have models that work well in both sample regimes, it is models in the third category that tend to be superior, at least as defined by this theory. And indeed, informed by this, we developed one such method that is based on Gaussian processes, so non-stationary Gaussian processes. And it uses these shared representations where the representations are indexed by this treatment assignment variable W. And we have two Gaussian process priors that can have different sparsity and smoothness. And their kernels are going to be this non-stationary Mattern kernel with automatic relevance determination. So hence we can learn the variables that are important for the two response surfaces. With this type of framework, we have a very flexible framework to learn representations for treatment effect estimation. And indeed, we are able to show that the IT estimation achieved by these non-stationary Gaussian processes is able to achieve in the limit the optimal rate. And it is able to achieve the optimal rate if only the relevant dimensions for F0 and F1 are selected, and the smoothness of the prior matches the smoothness of the two response surfaces. But how can we do that? How can we match this? How can we learn relevant features and smoothness of surfaces? We do that through hyperparameter optimization. And this may sound easy because you have heard a lot about hyperparameter optimization of machine learning methods. But for IT, this is tricky because we do not have access to the loss function. We don't have access to empirical PEHE. We do not have the counterfactuals. So what we do instead, we use an efficient PEHE estimator defined by Jamie Robbins as a cross-validation objective. And we use this estimator as the error metric to use to optimize the hyperparameter of the non-stationary Gaussian process. And in this way, we are able to match the condition when the number of samples goes to infinity, as well as account for selection bias in the small sample regime. Briefly, I'd like to say that another important topic that I'm not going to touch upon, but it is key in this treatment effect estimation setting, is how trustworthy are the predictions. So not only how accurate they are, but how trustworthy they are. In the NSGP framework, we use a Bayesian framework, so we are able to determine posterior potential outcome distribution and hence identify credible intervals, individualized uncertainty estimates for the predictions. So we know when we issue a prediction or for a particular patient of these two outcomes, we know how certain it is depending on the feature characteristics. However, credible intervals is not always enough. In many settings, people want to have true coverage and true frequentist estimates. For that, we need confidence intervals. And in recent times, we have built some work based on non-conformal prediction to be able to build confidence intervals associated with a variety of IT estimation schemes. And if you are interested in this topic, you can take a look at this work and you can reach out and we can discuss this in more detail because this is an important frontier of this particular topic. Now, I mentioned to you this non-stationary Gaussian process, and I mentioned to you that both we and others have developed many models. So you see here a variety of competing models, some from machine learning, some from statistics, some from econometrics, and the ones that have a pink arrow associated with it come from our lab. And these different models may be best for different observational data sets. So we would like to be able to know which model to select for a new observational data set. Ideally, we would like to automate the problem of causal inference such that at the push of a button, if somebody gives us a new observational data set, we can identify treatment effects using the best model. And indeed, this may sound simple, but the reason it's difficult is we do not have, again, counterfactuals, and we cannot easily do cross-validation. So when we need to measure these precision estimating heterogeneous effects, we cannot do this, we cannot validate the different causal models because we do not have access to an empirical estimate of the true loss function. So the way in which we have addressed this problem in past work was by relatively simple insight from Taylor series approximation, but then extend this type of idea from Taylor series approximation to functionals. So in an analogy to Taylor series approximation, we estimate the performance of a functional, so a function of a function, because we need to now approximate the performance of this causal inference model, which is a function of the data generation distribution. So we are going to try to estimate the precision estimating effect, treatment effects, so the loss functions of the true distribution, but we don't have access to that. So instead, we are going to synthesize that by using synthetic distribution with known counterfactuals and try to approximate that like in a Taylor series approximation. Because we have functionals, calculus rather than Taylor series, and we are going to use this von Mises expansion to do this approximation. So we are going to approximate the true loss function using this type of distributional approximation, and we are going to replace the derivatives in the Taylor series with influence functions. In this way, we can predict the performance of the causal inference model using the influence function of its loss on a similar synthetic data set. So if I have access to theta 0 and not to theta 1, and we are going to use this to approximate the loss function at theta 1. So if it is to use a first order approximation, we are going to approximate this inaccessible empirical measure by approximating it using accessible empirical measures and using the synthetic distribution as well as the first order. We can then determine the loss by synthesizing counterfactuals. So in a first step, we do plugin estimation. So we estimate the plugin model and the plugin PH loss. And then we are going to do bias correction, again, using influence functions. So in this way, we are able to determine how well treatment effect model is doing on this data set through this synthesis of counterfactuals, and hence computing the loss function. Using this approach, we then went to the competition on treatment effect inference, where a variety of data sets were provided for the competition and many models. And what you can see is that different models are best for different data sets. And you see, for instance, some of our methods which are doing quite well, but even then, it's only 17% of the time that a model like an SGP results in the best results. So different models are best for different data sets. However, this automated machine learning framework based on influence function is able to select the best model using this idea of influence functions 72% of the time. So this can now be used to identify which model we should use for a new data set. Let me now go one step further and talk about treatment effects over time, where we are not only using static data, but also longitudinal data that's acquired about the patient over time. Then we try to predict how to treat a patient, how to select a treatment plan over time, when to give treatment, and possibly when to stop treatment. So we want to do causal effect inference, but this time based on the longitudinal patient data rather than observational data that's static, like in the previous part of the talk. In this case, we have time-dependent patient features, time-dependent treatments, as well as static patient features. So this is the patient history that we can use, and on the basis of this, we try to estimate the potential outcomes. Note that again, like in the previous case, we only have access in the observational data to the factuals. We know the outcome given the treatment that is given. We do not know what would have happened if you would have given another treatment. So the counterfactuals are not known. And we try to estimate the potential outcomes in the presence of this challenge. And the challenge here is even bigger than for the static data set, because we need to deal with time-dependent confounders, which are going to bias the treatment assignment in the observational data set even more. What are these time-dependent confounders? They are patient covariates that are affected by past treatment, which then influence future treatments and outcomes. A good example in the area of cancer is side effects. So the side effects are going to be such time-dependent confounders. And we need to really learn in the presence of these time-dependent confounders that will bias the data. One way in which the literature has dealt with handling time-dependent confounding bias has been to use inverse probability of treatment weighting. And seminal early work in this area came from Robbins, Hernan, and Brumbach, who developed marginal structural models to deal with these problems in the longitudinal setting. A few years back, we extended these models using deep learning to a recurrent marginal structural model, which is a lot more flexible and it's able to deal with more complex relationships between features and features over time. However, all these marginal structural models, whether it is the conventional ones or the recurrent neural network-based ones, are suffering from numerical instability and high variance. So instead, we have recently proposed an alternative to deal with these time-dependent confounders by learning balanced representations, so treatment invariance representations in a latent space. We call this work counterfactual recurrent network. And the idea is to use sequence-to-sequence models to build such counterfactual trajectories, but with a twist. So first, why sequence-to-sequence models? Sequence-to-sequence models have been very powerful in the machine learning literature for translation. To translate, for instance, from English to Chinese or from English to Spanish. And this is what we are trying to do here, where we are saying we translate from the past history of a patient given one treatment into a new future, or given another treatment into another future. However, unlike in translation, the challenge here that we have is that of selection bias. How do we deal with that? So the way in which we are learning to learn this sequence-to-sequence architecture and deal with the bias problem is by building treatment invariant representations that are trained using domain adversarial training. So through this, we are able to debias the data. And this is the foundation beyond these counterfactual recurrent networks. How do these models do in practice? The whole topic of how to evaluate causal effect inference models, especially in the longitudinal setting, is by itself a research problem. But one way in which it can be done is by using semi-synthetic data. So data where we have really equations associated with the evolution of tumors given interventions. And this is a model from a relatively recent Nature paper, which we then take to data to estimate the parameters of the model. The advantage of having such an explicit model is that then we can play with different parameters that control the amount of time-depending confounding and understand the vulnerability of different methods given this time-depending confounding. What you see here is the performance of these counterfactual recurrent neural networks as opposed to our earlier version of the recurrent marginal structural models, as well as the original marginal structural models. And what you see is that the performance is quite a lot better, both in terms of predicting accurately the treatment accuracy, given different types of time-dependent confounders, and looking at the horizon in the future. So this tau tells you how much in the future the predictions were made. Also, we not only look at predictions in terms of treatments, but also the timing at which these treatments were given. And in that case, it's even more important to effectively deal with confounding correctly. Now, I talked about this IT estimation, and it is not aimed at replacing RCTs, but rather complementing them. So you can use these ITs during a trial, before a trial, as a post hoc analysis of a trial, or even before a trial to determine how to select patients. One of the important frontiers that I'd like to bring to your attention, I'm not going to talk about today, but it's an interesting area, is that of adaptive clinical trials. Increasingly, people realize that current way in which we conduct clinical trials is in certain settings ineffective. So there is an opportunity to build next generation randomized controlled trials which are taking into consideration unique effects and unique characteristics of patients. So for instance, even the dosage that we should give to a drug and adapting the dosage effect while a trial is given, or to identify how to recruit in subsequent cohorts patients for clinical trials. All of these represent important research topics. We are doing some work in this area, but the area is largely unexplored. So many new and good ideas are necessary to come in this topic. Now, before I finish, I want to use the next 3 minutes to talk about this idea of quantitative epistemology, how the humans make decisions, and just give you a brief flavor of one of the many things we are doing. So we use again the same idea of counterfactual estimation, but this time not to provide a decision support system, but rather to understand the decisions of clinicians. So what type of counterfactuals are in the head of the clinician when they decide to treat a patient in one way or another? So we are learning what if explanations of the way the clinicians make decisions over time. So in this work in which we try to understand clinical sequential decision-making, we try to explain sequential decision-making and build interpretable parametrizations of the clinician's behavior. And what we try to do is, for instance, we want to understand, do the clinician weigh more the way in which the the disease progresses? So are they aggressively treating because they focus on the disease progression and, for instance, reducing the tumor size? Or are they focused on the side effects, where being too aggressive in the treatment may reduce the tumor volume, but may lead to an increased side effect? So unraveling this trade-off and preference associated with the different actions of clinicians, some who may treat very aggressively cancer, some which may treat much more mildly disease, is important. It is important both to understand variation in practice that is desirable, so treatments that will be truly useful for the patient, as well as undesirable variation in practice, practice that can be improved, where clinicians can change their decisions on the basis of the information they have about patients over time to improve outcomes. So the goal in this work is to parameterize the reward of the actions based on the preferences over counterfactuals. So the goal is to recover these preferences, these different weights. So now the counterfactuals, so what we are assuming is, given on the history of a patient, the doctors will do in their head different types of what if estimation, counterfactual estimation, and decide would it be better to treat, when to treat, and how to treat, thereby putting weights on the different outcomes over time for this patient. And we are learning these weights from observational data. We are aiming to do inverse reinforcement learning and recover preferences over potential outcomes. We are, of course, in doing so, assuming that the clinicians are rational decision makers that are truly able to know the true potential outcome. So this relates to the area of inverse reinforcement learning, and because we learn from offline data, observational data, we are in the batch setting, where we have access to expert policies over time, decisions that are made over time, the features of the patient, as well as outcomes. And the focus is to recover the expert weights W star and the policies of the clinicians that are similar to what we see in the expert policies. In this way, we are able to do this counterfactual inverse reinforcement learning, where we have the potential outcomes and we use them to define the rewards in terms of these counterfactual outcomes, and then estimate a feature map from this batch data set with expert demonstrations to estimate these rewards. So the counterfactual outcomes becomes part of the inverse reinforcement learning process, where we are unraveling the decision making. So these counterfactuals are used to define these features phi that are enable us to estimate the feature expectation of the policies mu of policies, so the feature expectation mu over the policies that are candidate policies pi in this setting in order to estimate this reward weights. An advantage of this type of thinking, where we use counterfactuals for inverse reinforcement learning, as opposed to other work that has happened in the area of inverse reinforcement learning, is that by estimating these effects of different actions using counterfactuals, we can directly tackle the offline nature of policy evaluation in this batch observational setting. But also we can naturally accommodate setting where the expert policies will depend not only on the current state, but entire trajectories of disease. So unlike in a Markovian decision process or a reinforcement learning or an inverse reinforcement learning setting, which is Markovian, now we have entire history of observations that are integrated in the decision-making process. And we know that clinicians make decisions by looking not only at current state, but entire histories. This brings me to the end of my presentation, and I really feel there is a lot of need for applied mathematics in more diverse sense, to really work together with artificial intelligence and machine learning to provide a rigorous and robust methodology for deriving actionable intelligence to clinicians to better assist patients, to enable data-induced discoveries, enable integrating complex data sources, not only clinical data sets like I described here, but also high dimensionality data sets such as omics. And last but not least, do data-induced causal discovery to enable new therapeutics. If you are interested to see more research in this area, we have recently started in Cambridge, this Cambridge Center for AI in Medicine, which brings together very diverse group of people from machine learning to economics to data science in most diverse sense, as well as to clinicians and genomics researchers. So please take a look at what we are doing, and we are very eager to collaborate with people outside Cambridge and outside the center. So if you are interested in this agenda, please reach out. And finally, I'd like to advertise a postdoc position in my group. So if you are interested in this agenda, even if you are not a machine learning researcher, but you are coming to this area and you are interested to bring your applied mathematics skills to machine learning, please reach out. Thank you very much.